Ladies and gentlemen, we are plus or minus more or less sort of on schedule. Now we come to the point where we do reports from the breakout sessions, and I talked to Dennis Gannon earlier, who said that he certainly wouldn't need a full hour, so the fact that we're running behind is, I think, just fine. I'd like to suggest that we keep the breakout reports to order 10 minutes. And I think I'd like to also suggest this. A good order of operations might be give the breakout reports. Let's have Dennis share some wisdom with us after we do the breakout reports. And then there will be time for discussion, hopefully between then and when we wrap up at 5, and there will of course be chemical social lubricants, ethanol in whichever form you happen to like it best before dinner, and lots of time at dinner. So we'll do the breakouts now, and shall we start with the designing for usability or for sustainability? Seems like a good thing to start with because that is the beginning. So, Robert.
Hi, I'm Bob McGrath from NCSA at the University of Illinois. I've been asked to report on the discussions of reusability. Now, I've only seen these slides about once flipping by, so you'll have to pardon me as I may have to look at them carefully. First of all, we had, as it turned out, reusability turns out to be a rather complex concept, and so we had to thrash around a little bit to make sure that we were even talking about the same thing, which mostly we weren't. So this diagram was trying to capture part of this, which is there's a range of reusability, as in you can take something and use it again, even though you didn't write it. There's reusability, as in you can take something and use it again for another purpose. And there's also aspects of I can take part of something and mix it with something else. So there's a lot of different complex things in there. This diagram was trying to capture some of the examples we kicked around of ways that software might be out in the world that have different implications for reusability. So software as a service tends to be a all or nothing deal. You can do what you can do with it, but it's hard to change that. Virtual machines may be a little bit farther away from that on that end. Ruby on Rails was discussed as a good example of things that let you mix and match and reuse libraries to build new applications. And then there's extremely general frameworks. They let you do anything, but you have to do it yourself, was one of the words that was on the right of this diagram. So just that to give you a flavor of what kinds of reuse we were talking about. Yeah, so that's what this first part of this slide here. We sliced up the problem of reusability. There's at least two parts of that. One is that you're willing to reuse software. That is that you know it exists, that it's something you want to do, that it does what you need. I'm phrasing that. I'm not sure I understand the sub-bullets on the second one to explain them any better than I just did. And then, are you able to reuse software? So what abstractions are exhibited by that software? And of course, that gets into many technical issues of how software is organized and delivered. And we actually didn't talk about that very much, which I think there was a slide that was talking about that, and I don't see it here. So we actually didn't spend very much time talking about software, how you build it. We spent most of our time talking about software process and the implications of how it's done and how many people think it should be done. So we have this laundry list here of things that ought to be done better in the world. So software should be documented. It should be useful, by which I think it means it does something useful for the users. It should be reliable, portable. A lot of talk about portability. There's lots of dimensions of that, but fundamentally it means that you need to be able to move it across platforms and up forward through time as platforms and dependencies change. It needs to be sustainable. There was a lot of discussion about what kinds of things that might mean. Here it says how well supported. A lot of discussion about commitment, that there are actually people committed to supporting something. It's not a matter of just dollars. There was a key need for it being findable. So no matter how much software there is in the world, if you don't know it exists, it doesn't help you any. And the visibility is the flip side of findable. We had a lot of careful discussion of certification. We put that word in there because it's really important that you be able to find out how good software is without having to like investigate it yourself all the way down to the bottom. So we put one word, certification, in there, knowing it's controversial because it's got a lot of implications. And then we put some qualifiers here that what we're shooting for is measures and indicators of trust, assurance, quality. So this might be community-based ratings. This might be other kinds of ratings. So it's not necessarily some kind of police state thing, but it's not just advertising flyers either, right? And then we talked about some recommendations for revising processes so that reviewers can have reasonable information about software that was produced on a project, comparing it to if you do a research project and you turn in the several papers you did for this project, that's sufficient for reviewers to tell whether you did good science or not. But we need some kind of equivalent information about software that was generated so that you can tell whether or not this was successful and reusable software. So the technical issues, we discussed various kinds of the importance of abstraction and APIs, and to me those are highly related concepts. And as I said, we actually stopped talking about those because the other issues seemed more burning. So that's kind of an interesting finding in itself, that we felt that there were lots of interesting ways to deliver software. We knew an awful lot about service interfaces and APIs and frameworks and things like Ruby on Rails. So there's a lot of technical options. So we spent a lot of time talking about what processes should be done, not what technical options should be used. So here's, I think, this means recommendations for funding agency or something like that. Discussion of reuse is sharing of community resources, and so an example is telescopes. Infrastructure is different than prototypes. A lot of what we had to do was sift through the types of software that there are in the world and which parts, what standards should be applied, and what does infrastructure mean? What is infrastructure? What of all the software that we need in the world should be called infrastructure? And there was no complete agreement on that topic. I think that's a key. I think that's an undisputable finding from our discussion. One of the key things that came out repeatedly was the need for long-term commitment, both by funding agencies and developers. And here we're talking about commitment to maintaining software. So you don't have to keep proposing to put in new bells and whistles. It's okay to propose to do a good job of keeping this software alive. That needs to be possible, so it needs commitment by funding agencies, and they need to locate people who are really committed to doing that and not just creating some software and walking away from it. The funding agencies need to uphold standards for infrastructure. This is why we talked about certification and things, kind of come up with what kinds of things you might do to have metrics and publish them in the right ways, what kind of standards were needed, and then these standards must be incorporated in solicitations and reviews. So we only barely touched on those, but those are really important topics that I think we identified. Let me look at this slide for a second here. So I'm not sure what the first bullet is saying. Can somebody tell me what that means? Okay, we'll skip that for a second. Quality assurance. Obviously, we've heard about metrics. We heard about metrics over and over again in this breakout. We need to find interesting metrics and assess them and provide ways so that you can find metrics on software without doing it yourself. That is, I can go look up at interesting sites that will tell me that this is highly rated software in the following dimensions, and that will help me know whether I want to use it or not. And so that would feed into a substantive review. Then here we're talking about review of software. Okay, so we proposed to do something that's going to be software infrastructure, and then we said we did it, and you want to evaluate what we did and whether it's really worth incorporating as software infrastructure. So as we need metrics, and we need ways of reviewing those metrics. Lifecycle support, of course, is that it needs to be supported beyond the first iteration of development in both funding-wise and personnel commitment or institutional commitment. And discipline evolution support, I think, is referring to the importance of community driving these developments. So the communities need to figure out what kinds of infrastructure they need and when it has to change, and to drive the process of selecting. And that's our list. If anyone has any quick questions, I can reflect it back to other people.
I guess I have a quick comment.
Mm-hmm.
This presentation is completely void of who are those users, what are their requirements, what are their levels of support you want them to give you, how are you going to define those success metrics. Are they end users? Are they developers? Are they middleware engineers that need to integrate?
You're completely correct. Actually, there should have been at least a bullet on here asking that question, because it did come out a couple of times. We did not answer it, but we asked that question.
Yes, I just wanted to say that, because the users really, if you have people that are developing software and you want to sort of promote the best practices, you sort of get people that are tool developers that are going to be your developers at the same time. And then if you have application scientists, you sort of have, the applications are going to be the users of certain of the tools. And I think that's what you are saying, that we talk about it in the room about, who the users are.
So we've got those comments now. I think we suggested if we pause now, we will stay right on time and stay right on time according to the revised schedule as opposed to having to re-revise the schedule. So thank you very much. How about
Okay, can you hear me? Well, first of all, let me say that there's probably no summary that could capture the richness and diversity of the discussion that occurred in this room around this issue. Let's see if we can get the right slide up there. And so I heartily encourage the folks that participated in that discussion to provide the color commentary necessary to portray the conversation we really had, because we sort of ranged all over the place. I think there were several core dimensions that were really central to the discussion that I think we, while there probably wasn't anything resembling sort of a unanimous sense, there were certainly some themes that emerged. But I think the first one is, we said it in many different ways, and that is, to get serious about core infrastructure out of the, and I think a lot of our comments were focused on NSF here because I think most of the people in the community have had the most experience with NSF. We spent a lot of time, probably at my urging, looking at different kinds of examples, and one that we looked at was the CA Big project, which is a project of the National Cancer Centers that was really reflective of an instance where there was a domain community of researchers in the National Cancer Centers who had a history of not collaborating, of not sharing information, and a perpetual frustration that the investments that NIH was making in these programs was never really being brought to bear on the core problems. And so NIH pushed out a project they called CA Big that was really, I think, sort of in my history, the first time I've ever seen a federal agency really attempt to provide a top-down leadership, a coordinating infrastructure to establish an effective layer of cyber infrastructure. Now, that project is still, I think, in very much in the development stage, and it's hard to say how successful it will be. There are some cancer centers that are not participating enthusiastically. There are others that are participating quite enthusiastically. But I think the general notion was that what we really need, and I think there was a sense of that in every way from most people in the room, from our funding agencies, is more top-down leadership and coordination. To really establish expectations, to not do this in a way that can be easily picked off and picked at because it's perceived as being competitive with the domain science they fund, but that in the creation of special programs like the CI program, that it has to break out of the traditional constraints that are established around many of our agencies, about the relative balance of peer review versus agency leadership. And I think I think it was a consensus of the group is if we're going to make progress here, agency leadership is absolutely critical for us. And so I think that was one big kind of notion that we talked a lot about, and one strong recommendation. Then I think we spent a lot of time talking about, okay, what are the sorts of incentives you put into the system? And there were a number of suggestions and items that we talked about a lot. For example, separating the review process for core software to include, from the normal review process, not that you don't have peer review process, but that you create structures for review that are more likely to result in the outcome of the project being useful to the infrastructure underneath so many of the research projects. And that I think dovetails with this notion of stronger leadership. There are very few examples, I think, of where, a particular leader in an agency saying, this is how we're going to do things, have resulted in positive outcomes. There have been instances, in fact, where just the reverse has occurred. But certainly, leadership around organizing processes to select frameworks and approaches and organizing the appropriate people in the community into processes that result in real decisions and real choices that enable us to push forward is important. And that means, of course, providing options and incentives to transition software to sustainable. Now, in all of that discussion, there was one big issue that we really struggled with. And that was, you sort of see here in this next point, we talked about sort of, okay, how do you separate core versus domain-specific software? Can you deal, can an agency expect to deal with both of those in the same way? How do you separate research versus software development, for those kinds of research projects that, that have software development embedded in them, software development that has research embedded in it? How do you treat computer science, for instance? This sort of notion that I think as we talked about these first 4 points, that to bear in mind as we think about how the agencies can engage more leadership here, to recognize that one size doesn't fit all. There's diversity there. As you approach the problem, there's no single solution. maintain a lot of room for projects that can make impact and experimentation. There were some very specific examples, that recommendations that we talked about to actually change the scoring process for proposals that include software to include sustainability, recognizing that it's important, I think, to also have some mechanisms in place to assure that you're not investing a lot of resources in making stuff sustainable that may not be valuable as sustainable. There is a lot of software that gets done that is germane to a specific research problem and may never become sort of core software used by lots of people, but also some good arguments made in the room that if we are as scientists serious about the notion of reproducibility, which is, remember from the beginning of the time we learned to become scientists, one of those core concepts, to think then that we don't have some obligation to preserve, the software and the code and the data that went into these analyses is sort of kind of jumps right back in the face of the basic nature of reproducibility of research results. I think that there was another extensive discussion about how the agencies might build in structures to reward proposals for building upon existing software, and that there was a great role for the agencies to play there. And again, looking at NSF in communicating more across the research communities and across the domain areas, the program areas, about the availability of software. There was a point I think when our one poor NSF employee who was who participated very effectively in the conversation was talking about a communication with I believe you said a program director who didn't know what the TerraGrid was. And, if you've got that kind of disconnect between, core infrastructure investment and between the leaders in the domain sciences, that's not serving anybody's interest well. So I think, coming out of that is a strong recommendation on our part that the NSF has to be more aggressive in communicating across all of their science domains information about important CI-type projects and programs that were going on, and then the need to continue to make NSF investment in the development of maintenance models. I think we had another group that was actually talking about those concepts of, okay, what are the best models for maintaining? There are several models on the table. I don't know that there's any one, again, no one size fits all, but I'm not sure all of the work we need to be doing, all of the discussion and all the investment we need to make in not just defining models, but getting infrastructure in place to support those models has been made. And I don't think in the long run, leaving it up to the individual research participants in the process to create those infrastructures and to create those models and to manage them is likely to result in the kind of outcomes that we want to have. So those were the areas that we talked about. Others in the group or in the discussion that would like to contribute or identify anything I've missed? Okay.
So let's continue the discussion of the resources necessary to enable software, perhaps with the outcomes from the what other options other than NSF are there for funding software infrastructure. And I believe this was a group that didn't have a slide. Oh, okie dokie. Well, that's okay. Have at it.
And I found out 10 minutes before it was over that I got to present what we thought. I'm not sure what we thought. We thought about a lot of things. Yep, that's it. Thank you. So we pretty much had 2 ideas for everything. And so that was the first slide. So we had 2 types of development efforts, which kind of is what we heard from the earlier presentations. We sort of had research-focused apps, which are really domain-specific. People like Gerhard talking about the NanoHub and focusing on nanotechnology and developing apps that really serve that community well. And obviously there was a very successful model for that. And then we had the sort of middleware developers that develop things like MyProxy that we heard a lot about this morning. We thought about 2 phases of development. One is the chasm to adoption problem. Who pays for that startup? And second, who pays for it after it's been adopted and keeps it going? So this morning, Jennifer used the MyProxy example, which we all really liked, and we talked about quite a bit, and that laid out a really great talk about all the things you need to do to be technically sustainable. And then came the last bullet, which said, and then it's NCSA's problem to take care of it. And so that's okay, but what happens when there's no money to pay that person or persons? Who pays for it then? So we talked quite a bit about that. I'll share that, what we thought about that in a bit. 2 types of funding models, top down and bottom up. So the NanoHub is very much the bottom up, looks at the researchers, asks them what they want, builds a tool to meet their needs, and is very successful. Then you have the top down, which says we're going to build a hierarchy, we're going to impose taxes, we're going to do the following things, and this is how it will be, and was really heavy-handed. And we saw pros and cons to both. I don't know which side actually won that argument. I don't think either. And then we had 2 types of motivation, carrots and sticks. And I think we liked the carrots better than the sticks. Okay, so things we'd like to see. So from a middleware, so we'd like to see a forum for middleware developers annually or biannually to present what they do to the people like Gerhard at NanoHub, to tell them why he should care about them and why he should use them and why he will enable more researchers in his area by using them, and therefore he should take some of his grant money and support them. And we thought about this would be a great forum for all the people that are funded to do either research application development to come and to be forced to listen to these people, talk about their middleware, and then basically, you have a metric of success, and that is the research communities are willing to pay you because they're going to enable their research or not. And so you have a natural end of life for things that are no longer useful by the research community. The other thing that came out was this clearly might change the kinds of research computing that are funded, because the researchers will be driving it much more than the sort of computer scientists or people that are building large-scale systems. So that may be a good thing, it may be a bad thing. We know there's political reasons for doing both, but we talked about it. We also agree that there needs to be metrics and deliverables to any funded software development, whether it's middleware or application, with payment schedules. So if you get lucky enough to win a Track 2 award, you don't get paid till the users can use the machine. So why should software developers get all the money up front if users can't use their software, right? So you could build in metrics and deliverables and payment schedules. It's a little heavy-handed, but it would make things transparent. Developers would have something to shoot for and requirements, and the community would know what they're getting and what they're paying for. And then we said that we sort of like this idea of open source with standards, and standards is loaded, that allow/encourage researchers and corporate alike to develop and on top of them. So we use MyProxy again as an example. Microsoft has absolutely no motivation to pick up MyProxy. Right? So when the research community is done with it, it's probably dead. Why? Because they want you to use their interface for live meeting or whatever it is, or live, MySpace at Microsoft. So if you have open source standards that are heavily used by the research community that they can build on top of and enable their products to use those things, they're motivated to do it because researchers will use their tools as well in research, as opposed to saying, I don't want it. It doesn't interface with what I use. There's too many things out there that all the vendors provide that we'd like to see layered on top of what we need as fundamental software. And then the last thing was identifying the markets, right? So academia, if you're a researcher, you're faculty, you don't care about markets, you care about tenure. That's your carrot, right? But in the business world, what you care about is a volume market. Well, there's a fundamental disconnect there when you're developing software and trying to find someone to pay for it. So, the MyProxy example with NanoHub, Gerhard said, if these people could stand up and show me how NanoHub's going to bring another 20,000 users to NanoHub, and they need it, and it enables them, I'm going to take some of my NanoHub funding and make sure they get it, because it's going to make my software better. But if they're not, why should I? Right? So that's an example of a market that wants to use the NanoHub resources, and therefore there's a reason for people to use money to keep those things, to make those resources better. Did someone want to add something? Sorry. So we also talked about a tax hierarchical model, and the problem with that is that people have to see a value in their 1% software tax on their grants, and that did not resonate well with the researchers. It resonates great with the developers because they go, cool, we're set. We just keep doing our good work. NSF says, yep, you're doing the right thing. We go to the TerraGrid meetings and they say it's doing the right thing. But there's no built-in metrics or feedback mechanism from the research communities that go, why are they getting all that money if it's not helping me? And so we also, lastly, and we did not have a lot of time, we talked about foundations as a coordinated approach to post-adoption support, and we didn't get too far down the path on that, but I think that's everything we hashed out. Is that right? Anyone else want to add anything? I can't believe it if you don't. I was usually wrong through most of everything I said, so they... Okay, thank you.
Dave, thank you very much. Moved from Cornell past to Cornell present, and now we're going to go to Fairbanks, and Jeff is going to talk about the reforming the educational system and the tenure system in the process. So this is the last of the breakouts, and then we'll go to Dennis, and so far so good. So Jeff, take it away.
We had a very intimate group. There wasn't a lot of back and forth. We all sort of came to an agreement as to what the problems are if we want to get to sustainable software. So the end goal is we want to produce students who have a certain set of skills who can help produce long-term sustainability in terms of science software. So understanding the code is being deployed for purposes other than the needs of the people who are writing the code, right? I mean, the underlying thing is science. We all want to produce better science, and software is just one mechanism to get there. We want them to learn how to work on modular systems because science codes have a long legacy, right? You end up making small changes to a bigger work. It's not monolithic across disciplines. And we want to try to have students appreciate a coherent set of practices, not necessarily best. You can't really describe best practices, but in terms of a consistent project development, a lot of things go together to make sure that you can have a sustainable cycle, lifetime support, and release characteristics. So part of that discussion was talking about trying to get students some practical experience. And let me read over the slide. So right now, the scientific codes that we sort of talked about aren't necessarily using those practices, and we end up with some sort of very brittle codes or codes that end up being forked off, and so you have 3,000 versions of the same underlying science code, but they've been tweaked for an individual researcher's needs as they acquire the codes. And that's not necessarily what we think about in terms of sustainability. And so we want to try to get some methodologies into the education so that people don't tend to do that anymore. They tend to put adaptations back into some sort of framework. So and then come down to curriculum development. So software engineering is what we try to think of this as. Is a discipline in its own right, and and we have to include some aspects, not just programming. It's everything other than the programming, right? It's trying to deal with things in a collaborative way where we focus on teamwork and collaboration and using more modern concepts like repositories and code revision controls. And one thing that was focused on is actually working on specifications and deliverables and inputs and outputs, and not just writing some code for yourself that no one's ever going to see. And with that, coherent testing plans, and just as important, we were talking about, if you look across all the science code that ends up being developed, how much of that is developed by traditional computer science people versus people who start with domain-specific knowledge in their research field, and then they have to build codes later to get their research done. And that's I don't know the answer to that. I don't think we have an answer to that. There's certainly a mix, right? Some more of the infrastructure stuff is clearly being done by computer science professionals, but somewhere up the stack that switches over to domain-specific, and they need to know how to do this too, because it's an end-to-end deliverable. Sustainable software is not just the lower pieces, but it's going to end up being what can you do from a research standpoint, and that goes all the way up to the things that I have to write as a physicist. So how do we make the changes? Well, one thing is to influence the community recommendations that are impacting curriculum development. For example, the ACM doesn't necessarily talk about things like collaboration and teamwork and sustainability concepts when they talk about what makes good curriculum. And we maybe need to have textbooks that focus on the practical ideas behind sustainable software that's showing up in the real world. And we recognize that this actually is a fast-moving target, so this could be a problem. And we want to try to stress the idea of sharing as much material as possible. The Rice Connections project was brought up, and then I brought up the fact there's a new collaboration that's going on that's trying to interface academic educators with people who have open source real-world experience and try to develop a curriculum that makes sense to teach the skills that the people who are working on these larger projects want people to come in the door with, so they don't have to train them all the skills on the job. And of course, change the tenure process, but you can't do that, right? So we have to figure out how we can get new ideas into the curriculum in a more efficient way. Because new ideas are a challenge. In fact, because this field is moving so much faster than sort of the traditional hard sciences, we all know how to teach a freshman physics class. It's the same thing for the last 15 years. There are some people who do it better, but it's not as fast a moving target as what we think of in terms of the skill sets that we need people who are doing science programming going forward. And so, how do you make incentives for that sort of hard work? And how do you make it easier? So how much curriculum sharing can we do in the development phase? And do we have to think about traditional textbooks, or is there another way to do that that people are willing to pick up? It's the kind of thing, what we don't know is how many people who are sort of off trying to do this now, and there are people trying to do this. It's a matter of do we have enough that can work together and create a new type of curriculum that addresses this. And it's absolutely interdisciplinary. It's not just the traditional CS student. Everyone who's doing research in the domain-specific field needs to learn this, because they're going to be reading code, they're going to be writing their own code, because at the end of the day, they adapt what they need to do the research that they're doing. And so this sort of fits in after what is a variable, what is a for loop. This is how do you structure building a project so that you're doing it in a way that adds value. You're not just doing it off on your own. And that's that's what we're sort of getting at. We want to talk about adding value and teaching not just students but faculty how to add value on top of other work so that it can last for 10 years and still be relevant. So I think that's the core of it.
I wasn't in your discussion group, so I'm curious about the statement about the ACM being unresponsive to curriculum change.
Well, not unresponsive, but there has to be a discussion at those groups who are discipline specific groups, so we can, because let me say this as politically sensitively as possible. It's not that they're in the way, it's a matter that they can lead a change. It's a matter of driving the discussion up into those into each sort of overriding advisory group, because in some ways they set the curriculum, like what needs to be in the curriculum. And if we recognize that sustainability is important to do research, then the people who are impacting what curriculum needs to look like needs to also understand that. So ACM needs to understand that. I imagine APS needs to understand that. I mean, we have to go up into the disciplines so the discipline advisory groups can come down and impact what curriculum needs to look like, so that we're all learning sustainability as early as possible, so we don't have to relearn from bad habits.
I have a comment regarding teaching programming. I was very shocked when I joined Purdue 5 years ago, again, after being gone for 15 or so. We have about 50 theory students sitting in one major area. About 48 of them do their work in MATLAB. 2 of them are ostracized people that actually know C or Fortran, and they know what MPI is. And that's a real world thing of probably a really good computational electronics group. To teach them what SVN is and what debuggers are is like crawling up the wall. And from my personal experience, I learned how to develop software almost like an apprenticeship. I was paired with a senior graduate student who knew Unix, and I got my Unix command of the day, so to speak, and looking over somebody's shoulder. That culture is completely gone.
Well, I think...
And you can't remedy it with classes.
Yeah, and I agree with that. I don't think I stressed this, but what I talked about a lot, because where I'm coming from, there are people inside the Fedora community who are trying really, really hard to reach out to academics and bridge existing open projects and have them be an opportunity for students to do practical work. It's not scientific work right now but it's a general computing open source projects that are out there, the larger ones. They really care about trying to get students in the door and teaching them how to do things in a certain way so that they're more effective. So it is to affect that culture. But I don't know how to do that inside research science, because you're right. And even in my group, I work with double E's, and they work with MATLAB, and I'm trying to write C code and Python code that I know can be ported outside, so we can use it in different environments, and I know we have to.
So, no, excuse me. I've got the microphone. So I really couldn't disagree stronger with that previous comment. I think we should be celebrating the fact that we can have effective researchers in a technical field who don't need to know about debuggers and subversion code and are able to use things like MATLAB and higher level tools to be productive and to be much more effective in what they do. That's wonderful. Why there's the obsession that everybody has to rebuild their Linux kernel or have that ability to do that and so forth, or along those lines? I do not understand. Is it necessary?
Can I just comment on that? Like, I am definitely an open zealot. I'm not going to lie about it. But I don't think the discussion is so much about which tools or languages you're using. It's the methodology of doing things in that anticipates highly collaborative work, so that people are using revision control, because those are the concepts more than the language that is really making the open source ecosystem work. Is the fact that it's highly collaborative, and that is right. And when you have 1,000 people or 100 people all doing small changes, even though you might have one person who does the bulk of it, if there are 100 people making small changes, small bug fixes, that breeds a certain level of commitment to keeping things, a history of contribution and things like that, which I'm more concerned about that than I am concerned about MATLAB specifically. No, I'm concerned about a collaborative environment. Can you point me to an openly collaborative project that is based on MATLAB right now? I can point to a lot that's based on C and Python, but if you can, that's great. That could be the basis of curriculum. I'm not picking a project. I'm saying any project that is highly collaborative and has these sort of things that you have to deal with are the skills. It's not the exact code. It's the skills, so that when you go off and start something else and you have to work inside someone else's framework, and now you have to do C, may not know C, but you know how to collaborate. And that's the fundamental thing that we're trying to talk about. Right. But well, I can't say no. We're not doing it. That doesn't say that we can't do it. It's not to say that the most effective way to do it doesn't involve classrooms. I think the people I work with from a volunteer standpoint, they're very interested in trying, because they know how hard it is to get people up to speed if they've never done it before.
So let me suggest this. Last word from Stan, and then we'll hear from Dennis, and then there will be time and alcohol with which we can continue hearing on.
In that case, I will make my comment extremely brief. So I just wanted to comment. I spent a lot of time trying to get people onto my supercomputer using MATLAB, and that was a arduous task. But now I think the number 2 or number 3 most used package is MATLAB, and not in serial. They're using parallel code. MATLAB's version of parallelism. But more importantly, I think as to the topic here. As we move our way up the food chain of more sophisticated, denser languages, the requirements to do a good job of development and commenting and understanding how to be able to go back and use it again years later is all the more important, and that's something that we need to be thinking about. And in fact, one of the white papers I know, because I happen to read it, talks about embedding comments and being able to extract those comments automatically to be able to document your code, things like that. So I think it's a very germane issue.
Yeah, I could talk at length about proprietary versus not proprietary, but I won't, because that's not the point. The point is the skills of collaborating and doing that efficiently. And maybe you can't do it in the classroom, but I think it's worth trying, because but it's a matter of teaching the faculty how to do it, right? Because effective education is because you have effective instructors. And right now, how many instructors use these processes in doing their own work?